Welcome to another RDWorks Learning Lab. Well, over the last couple of weeks, I've come across some interesting observations. You know how you look at things, but you never really see? Today I'm going to hopefully take you through some experiments and thought processes to reach quite an important conclusion about the way in which our laser beam, the mechanics of our laser beam, actually work. The conclusion that I've come to answers lots of little loose end questions that I've had over the past year or year and a half. Now, we've already started to work on it last time when we looked at energy density. We looked at the way the energy gets amplified through a lens. We go back a couple of 3 sessions before that when we were doing 3D engraving, and one of the things that I developed at that point in time to help me with assessing what range I should be using for my max and min power, we developed this little matrix of parameters where the speed was 400, 300, 200 and 100, and we had 10, 30 and 65 for the cutting power, so that we could see what the effect of speed and power was on the burning of wood, because we wanted to try and, when we were doing 3D engraving, we wanted to keep the burning as little as possible and the cut as deep as possible. I use the word burning because we have already established over the last session or two, when the light energy hits the surface, it turns into heat energy and interacts with the material. Well, if the material is wood, wood and heat means burning, as we can see clearly in this example here. Now, when I was doing some further work using the same matrix, and basically ignore the bottom 2 lines here, and it's these block of 12 at the top here that we were interested in, or I was interested in, because basically what I had a 2.5 inch lens, a 2 inch lens and a 1.5 inch lens. I wanted to try and see what the difference was when I used each of these lenses to burn exactly the same program. One significant observation that I made, and let's just take one of these blocks as an example, this block here. So it's 1, 2, 3 down, 1, 2, 3 in. We can see that it's about 1 millimetre deep, and that's with a 2.5 inch lens. And it's I don't know what colour you'd call that. Let's call it a light straw, should we? A light brown. And then we jump across to the same thing in here. And this is a 2 inch lens, which technically is a more concentrated form of energy. But first of all, from a comparative lightness point of view, this one is actually a lighter burn than that one. And in addition, this one at a 2 inch focal length should have been a deeper burn. But in reality, this one is about 1 millimetre deep, and this one is 3/4 of a millimetre deep. Now hang on, that doesn't make any sense at all when you start looking at that. There's a problem there that I couldn't comprehend. Why is it that a 2.5 inch lens cuts better than a 2 inch lens? And then we go across to the 1.5 inch lens, where we'd expect it to cut quite deep. 1, 2, 3, and sure enough, it is about just over 1 millimetre deep, but it is a horrible burnt colour. These two, relatively speaking, are correct in relation to each other, as I would have expected. This one is not. So why is this one so much deeper than that one, when it shouldn't be? Well, when I look closely at my 2.5 inch lens, which I've had for the best part of 2 years now, when I looked at it closely, I find that it's actually a meniscus lens. We were talking about the way in which the focal length of a meniscus lens is a slightly more compact focal point than a standard plano convex. Well, here is a classic example of just how effective that concentration of energy can be, because that 2.5 inch focal length lens is cutting deeper than the 2 inch lens. It's also cutting slightly darker than the 2-inch lens. Okay, so that's one question that popped up, and I was able to easily explain that. But the other question that I can't explain at the moment is this, and I'm going to give you a quick demonstration. Well, I don't think there's any doubt that's heat. This is a thin piece of plywood, and if I apply this heat to the plywood and hold it in one place, it burns. There's no miracle in that, is there? But look what happens when I start speeding it up. That same flame, same distance away, disappears. Now, there's two things I want you to observe there. You saw that burning, and what it's done, it's produced carbon. As we moved it along faster and faster, we've got some brown in there, but as we moved along faster and faster, it's disappeared to nothing. Now this comes back to the term that I described last time about energy density per unit of time. The energy density in that flame was high enough to burn that wood, and we saw it was burning. Actually, what it left behind was carbon, because the cellulose in the wood had been burnt away. And then as we started to speed up the beam, of the same beam energy, the energy that was available to burn any specific point was for such a short period of time that it didn't have a chance to do a proper burn, and all it did was to scorch less and less and less and less. Okay, so that's a very simple observation. Okay, now I'm going to fire the raw unfocused laser beam at this piece of wood. I've got it set to maximum power, and I'm pretty confident you will be able to guess what's going to happen. Now, let me do it again on the same spot. I don't know whether you can see what's happening right at the centre of that spot. That is glowing white hot. Now, why is it glowing white hot? Eventually, I will be able to make it glow. I've got spots before my eyes, just like looking at the sunshine. That shows you how bright it is. Okay, so now it's dimming off. Why is it dimming off now? Well, the answer's very simple, really. There's a hole in it. I've burnt my way through it. I cannot do that with a flame, because there is just not enough energy in a flame to be able to do that. But the other thing that you can see is I've burnt a hole through there, slowly, but I've burnt a hole through there. But what have I done around the outside? Now, you remember my picture of the energy profile across the beam and how the energy is concentrated in the centre of the beam? Well, carbon is a very good absorber of infrared energy because it's non-metallic, and anything that's non-metallic is basically a good absorber of infrared. And so the infrared energy that's been thrown there is converted into very, very high temperatures, because carbon can exist in a solid form until it gets to about 3000 degrees C, and then it turns into a gas. It is something that is truly called sublimation, Now, I've used that term loosely up to now to describe various other things that are going on, but basically most of the other things that have been going on have been evaporation or vaporization, should I say. Sublimation is a very exact scientific term that basically means an element or a material does not exist in a liquid form. It turns straight from a solid to a gas. And what you're seeing here is not smoke, but in fact it is carbon sublimation. It's the gas that is re-condensed on this surface here as it's been. I was trying to blow it away to keep it going in the opposite direction, if you remember, but the carbon gas itself was so hot that it went upwards. So there's the hole that we burnt through there, and you can see around the edge here that it is only just starting to dip in, and round the edge here it's black, and then right round the outer edge it's brown, scorching. But in the centre here, where it got really white hot, it eventually worked its way right the way through. But you saw how long it took to burn its way through there. It was what, best part of a minute? Here we are looking at my matrix of burning samples, and I think you'll have to agree that, look, I have removed probably 1/2 to 3/4 of a millimetre of wood here in one go. Does that look burnt? Is that scorched? How can I remove 3/4 of a millimetre of wood without burning it or scorching it? That's the obvious question that's been staring me in the face, and I have not recognised that that's the question I should be asking myself. How can I remove wood without burning it? There definitely are parts of this sample here where you can see that I have done burning. They're not the ones that I'm really interested in. These are the ones that I'm interested in. These here where I've definitely removed wood and I have not burnt the underlying layer of wood. To remove wood, normally you'd expect it to be finishing up like these examples here. Let's try and answer that question, should we? Because that's something that I've been wrestling with. Now, I've turned the air assist on now because I don't want the smoke and the heat energy to go back up and damage my lens. We'll see how long it takes to burn its way through the wood. How long was that? 0 time. Let's do it again. But it probably took less than half a second to burn through that piece of wood. But what I'm now going to do is the same thing again, and I'm going to be leaving the energy on for maybe 1 or 2 seconds. That one was about probably what, 2 or 3 seconds. That one was half a second or less, and that one was probably about a second. Well, you can see immediately that that hole has grown in size relative to this one, but it's the same beam. So how can it produce a bigger hole? What you're seeing with the outside of that very small hole is this ring of burning the lower energy part of the beam that has not been allowed to burn for long enough to actually produce a wide scorch mark, but it has started to produce a scorch mark around the edge of the hole. So the edge of the hole has burnt. But hang about, did you see the centre of the hole burn? What did you see? Did you see the white flash? So what I'm saying to you is that that white glow that you're seeing there is the same white glow that you saw here at low energy densities, but the energy density was so low here that although we were able to produce 3000 degrees C in the centre here, it wasn't sustained enough to force its way through quickly. Now, we've amplified this beam, this energy beam, by a factor of at least 3000. So consequently, it didn't take best part of a minute to burn through that piece of material, and that is probably only a tenth of a second if we listen to it in real terms. Click. After a tenth of a second, it's burnt its way right the way through. What it's actually done, it's vaporized the material in the center of the hole, turned it to carbon and vaporized it. So why haven't we scorched these? Well, the answer is because we have actually vaporized the wood. There has been no time for any scorching to take place. We've run at such a high speed, 200, 300, 400 millimeters a second, that the energy density has been captivated just there in the center of the beam. And we've got a very narrow beam of energy, but very, very intense energy, which has scoured the surface off, vaporized the surface without burning it. Why 65% here looks very, very brown, and here I've got another 65%, different parameters, 65% power, still done at 400 millimeters a second, but look at the difference in the color between that one and this one, and this one and this one. What was the difference? Well, all of these two rows at the bottom are 65% power as well, but this row here was done with a increment of 0.1. These were all done with an increment of 0.15, and this was done with a 0.05 increment. Now, bearing in mind the spot size of these lenses changes, and so consequently when we start running a 1.5 inch focal length lens at high speed, we actually produce a very thin line, and so consequently running this 65% here at 0.15, so what we're doing is burning a groove like that where the grooves are actually 0.15 apart, but the energy density is dropping off towards the top of the groove. We're burning a very deep groove in there. We're getting a scorching on the top of the groove, which is what you can see, but down at the bottom it's clean. So if I very gently remove some of the material there, look, you'll see, just touching it, I can break away the brown that's on the top of the groove, and you can still see the grooves, the bottom of the grooves, in there. So the colour is actually sitting on the tops of the V grooves. And so consequently what I did, I tightened up the increment to 0.1. And look now, 0.1 is more or less the same colour as the bottom of that one. I've now closed the grooves up so they look like that. If I go a little bit tighter at 0.05, I've probably gone just a little bit too far, and now probably, if we look, I'm actually producing a little bit of scorching because I'm double burning. But there are several interesting lessons that came out of this research. If you get your speed and your increment correct, you can produce a nice, clean, deep cut. Look, this cut here is about 1.5 millimeters deep, and it's no different in colour to this one here that is about 1 millimeter deep. I'm able to get 50% more depth with the same power, 65%, and faster, 400 millimeters a second. Understanding how wood cuts is very important. Now, it also answers another intriguing question which has puzzled me for quite some time, and that is about cutting wood. My parameter goal is to cut the wood as fast as possible. Set the power to maximum, set the air assist as much as you can, and run at the fastest speed that you can to allow your cut to take place. If you do that, you will produce nearly a char or a burn-free cut. Now, it won't be perfect, but you won't get very much charring on the edge of your cut. That's a fact that I established probably a year ago, but I've never actually understood the reason why. Now that we can understand the mechanism that takes place, we can clearly see that what's happening is, with the maximum amount of power with a fine focus lens, you're punching your way through the wood as quickly as you can with this high energy part of the beam, and you're not allowing this lower energy part of the beam that's out here to stay and linger and char the edge of your cut. There will be a small amount of charring, but the faster you can move the cut on, the less charring you will get. I give you that as an example. Again, unit time for energy density. And what we're basically doing is diluting the energy density in this weaker area around here, and we're only allowing enough unit time for this very, very high density centre part of the beam to burn through your wood and not to char it with this lower energy density that's sitting on the outside of the beam. Well, I hope that's explained a lot in a very short time. It's been a lot easier for me to explain it to you than it was for me to establish it and explain it to myself. I had to go through several mental acrobatic sessions to try and work out exactly what was going on and how I was going to demonstrate it to you guys. But I think the way that I've demonstrated it hopefully has clearly embedded it in your mind so that you cannot and will not overlook the fact that wood vaporizes. If you control the parameters right and this magic thing called energy density, then you can evaporate wood as opposed to burning it. Now, if you want to burn it, as you might want to, for maybe 3D picture engraving, which is very, very light scorching of the surface, then maybe this helps you understand how you can do that with very, very low power, a very, very soft lens, maybe even a 4-inch lens, to get the energy density right down so that you don't do too much damage to the surface, but you get scorching rather than evaporation. Too much energy density and you'll get evaporation. We might have to look at how we can produce this scorching effect now for 3D engraving. Every question we answer opens up several more opportunities for questions to be answered. Can I see an end to this? The interesting question is, will I wake up dead one day before I finish this work? On that happy note, thank you very much, and I shall be seeing you in another session.